Hello, honors chemistry students. In this video, we're going to go over notes 7 and 8. And note 7 you may have already done, but it's really important for notes 8. If you get these two sets of notes down and you take this seriously, like I know you will, then you are going to set yourself up for so much success in second semester. So it's a lot of work right now, but I promise you will see the rewards and it will pay off in second semester. Okay, when we name cations, how we do this is we are just going to name the element and then put the word ion after it. Okay, so that should be easy enough. So this is aluminum, but because we see a charge, this is going to be the aluminum ion. And let's change it to there, see if this is a little bit better. Element B, this is barium, but because we see a charge, this is barium ion. And this should not be surprising. What I have in front of me is my laminated periodic table. I hope you do as well, because you're definitely going to need that. And if I look at the box of barium on the periodic table, barium is element 56, symbol is Ba, and its average atomic mass is 137.33. And what is really kind of hard to see is that on the barium, you're going to see a little charge, and it's going to be really small, but it's going to say 2. And that means that barium forms a +2 charge. Okay? That's going to be very important. So when I see barium here as Ba +2, I'm not surprised at all. Cesium is going to be the cesium ion. Now, if you have an element that is multivalent or has multiple possible charges, we would know that because if we look at their box on the periodic table, so iron is the example I'm using, and I would be looking at your iron on your laminated periodic table, we're going to see 2 and 3. That means iron could be Fe +2 or Fe +3. Iron has multiple, just 2. We sometimes get to some really crazy elements. If you find box 42, this is molybdenum, and molybdenum is 95.94, and it could have 6, 5, 4, 3, or 2, meaning that we could have molybdenum +6, we could have molybdenum +5, we could have molybdenum +4, we could have molybdenum +3, or we could have molybdenum +2, and that's really kind of a lot. So if we said, for example, molybdenum, which is spelled molybdenum, which is kind of a weird word, we can't just say the molybdenum ion, because whoever looks at their periodic table, they're going to be like, okay, which one did you mean? Did you mean 6? Did you mean 5? Did you mean 4? Did you mean 3? Or did you mean 2? So when we have a multivalent cation, and these are actually only true for cations, we're going to have to make sure we say, for example, that this is not just the iron ion, but we're going to use Roman numerals to indicate the charge after the element's name. So this is iron 2 ion. In E, we have Fe +3, so this is going to be iron 3 ion. Titanium, that's element number 22. You've got to find it on your box. We know that this is going to be titanium ion, but in the box of titanium above the symbol, it says 4, 3, or 2. So it is multivalent, and so because we have +2, we're going to have to call this titanium 2 ion. If we look at scandium, scandium only has 3, so this is not multivalent, or it could not have multiple charges. So this is just the scandium ion. Silver, element 47, is Ag, and it only has a 1 above it for its charge. So this is just the silver ion. I will tell you, transition metals tend to be multivalent. Not always, but they tend to be. Okay, let's keep rolling here. Sodium, element number 11, find it on your periodic table. we look at the charge, it's sodium +1. All alkali metals are +1 charges. Here we have manganese, that's Mn. And manganese must be multivalent because I see a Roman numeral charge, so this must be manganese +7. Now, you could also write this manganese 7+. Both are correct. And then we have zinc. We find it on the periodic table. Zinc has a +2 charge, and that's it. It's not multivalent, so we don't see any sort of Roman numerals. Roman numerals are only for multivalent cations. Multivalent cations, okay? So only metals could have Roman numerals. Now, anions, these are things that form negative charges. Anions are named by dropping the last syllable of the element and then adding the suffix "ide." Some of them take a little bit of time to get used to. So, for example, fluorine goes to fluoride. Chlorine goes to chloride. Chances are you've heard of both of those before. But carbon, you drop the last syllable and it actually goes to carbide. Oxygen goes to oxide. Nitrogen goes to nitride. Phosphorus is a little bit weird. We actually drop the last two syllables on phosphorus. It's kind of an exception. And phosphorus goes to phosphide. Sulfur is one that we see a lot. Sulfur is going to go to sulf and then sulfide. Okay, and there's a lot of them. Some of them are just kind of weird. So, for example, selenium, and I'm going to struggle to spell selenium off the top of my head, is going, and I believe that's an E, actually. And it's going to go to selenide, which is just kind of weird. You don't hear that often. We're going to use this a bunch. Okay, so notes 8 may be the most important set of notes in this whole unit because we're going to use this forever after we've learned it. Okay, and we're going to learn about ionic compounds. And an ionic compound is a compound composed of ions that are held together by electrostatic forces. Electrostatic forces are just positives and negatives that are attracted to each other. When we form an ionic compound, the compound is going to be neutral overall, but it's going to be combined in a way where the total positive charges cancel out the negative charges, so we end up with no net charge. An easy way to represent that you have an ionic compound is that you have a metal is present. And ionic compounds, you see them all the time actually in life, so you see iron oxide oftentimes if you see rust. You see copper oxide if you ever seen like copper that is kind of turning green. You see sodium chloride, that is salt, table salt. That's an ionic compound. And they're typically going to be hard solids with high melting points. And ionic compounds are not molecules. They're just not. They are referred to as formula units. And a couple things that we'll learn about, not necessarily right now, but ionic compounds tend to dissolve in water and then break apart into their ions. And if they don't dissolve in water, that's just referred to as being insoluble. Okay, our goal with this set of notes is to understand how the formulas of ionic compounds are formed. This is going to help us out because we're going to do a lot with ionic compounds later, and we're going to need to know the formulas. Okay, I'm going to show you a couple different methods on how we're going to name these. Okay, if we see a formula and we want to know the name, we're going to say, okay, this is calcium. And so calcium as an ion is going to be called calcium ion. This is nitrogen, but as an ion, that is nitride. And so when we combine them, we're going to just drop the ion name, like we see here, and we're just going to get calcium nitride. Okay, that is how that's going to be combined. Now, another way that we can do this is we could say, okay, well, how do we write the names, or the formulas from the names? We have lithium. We look on the periodic table and we see on the box of lithium, element number 3, lithium forms a +1 charge. Okay, Okay, you need to be looking at your periodic table to get that, unless you just have those memorized, which chances are you don't. And that's okay, but you need to be using your periodic table. We find element number 8, which is oxygen, but we have oxide, so that means we have the ion. And so what we're going to do is we're going to say, okay, Li plus 1 and O2 minus. Ask yourself, how many positive 1s do I need to cancel out a negative 2 in order to become neutral? And the answer is I'm going to need 2 lithium plus 1s, because plus 1 minus 2 gives me a net charge of 0. Okay, we can use this using the crisscross method. Li plus 1, O2 minus. What we're going to do is we're only going to take the numbers. We're going to take this 2, we're going to bring it down and make it a subscript of Li. So this is going to be Li2. We're going to take this this 1 and make it the subscript of O, and so this will be O1. Typically, we don't write subscripts if they are 1, so this would be Li2O, and that O is just assumed to have a subscript of 1. Okay? If we have charges, which we always are going to do, and they're the same number, then they are going to combine in a 1-to-1 ratio, so there will be no subscripts. So for example, ask yourself the question, if I have calcium plus 2 and I have oxide 2 minus, we get those charges from the periodic table. Ask yourself plus 2 minus 2, those add up to just be 0, so they cancel. So you can crisscross these and say Ca plus 2, O2 minus. We're going to take this 2 and put it with calcium, so we get Ca2. We're going to take this 2 from calcium and put it with oxygen, so we're crisscrossing them. We get O2. Those reduce to become CaO. Okay. We want to just practice with these. Another way is we can use the reaction method. So if you don't like the crisscross method, then let's check out the reaction method. So first of all, if we have things in words, so potassium sulfide, we first want to make sure it's ionic compound. Potassium is a metal, so that is an ionic compound. Anytime you have a metal present in your formula, this is an ionic compound. Now, what we want to do is we want to figure out the elements or ions present. So we're going to go to potassium. We're going to look at element number 19 on the periodic table. We know that potassium is K, but because it's bonded with something and it's an ionic compound, it's really in its ion form. So the periodic table tells me that that is K plus 1. Sulfide, we look at the periodic table, element 16, that is S, and it has a minus 2 charge. Okay, so how we can add this together is we can say, okay, we've got potassium with a plus 1, sulfur with a 2 minus. Do they cancel each other out? They do not. So we're going to need 2 potassiums or 2 positive 1 charges to cancel out the sulfur or the sulfide S2 minus. So this becomes K2S. Okay. When we do this, we would get the reaction method and we get something that looks like this. Oftentimes people prefer the crisscross method. I know I prefer the crisscross method, but the reaction method is great as well. What I'd like you to do is just think about which method kind of flows in your brain a little bit better and stick with that method. Okay? So let's do some practice. Here's how I'm going to do this. I'm going to look at the periodic table and I'm going to say, okay, lithium, this is Li plus 1. Oxide is O2 minus. I'm finding these on the periodic table. I'm going to crisscross them. Take this 2, give it to lithium. We get Li2. Here we have plus 1. We're going to bring the 1 down there. We're not going to worry about the plus. We're going to get O1. And this is probably going to be written Li2O. Okay? If there's no subscript written, it is assumed to be 1. Next, we're going to look at beryllium. Find beryllium on your periodic table, element number 4. Beryllium has a plus 2 charge when it is in an ionic compound. Oxygen has a 2 minus charge or a minus 2 charge, however you want to write it. Ask yourself if those charges cancel each other out. Here they do. So our formula is going to be BeO. Let's say you do the crisscross method. No problem. We get Be2. Then we take the 2 from beryllium and we give it to oxygen and we get Be2O2. This reduces to BeO. Okay, we find aluminum, element number 13 on the periodic table. Aluminum is Al plus 3. Arsenide is arsenic, or element number 33, and that's As. As, according to your periodic table, will have a -3 charge. Those two guys reduce to become, or they crisscross, or they cancel, however you want to say it, Al3As3, and those guys reduce to become AlAs. Now let's keep practicing. Sometimes it takes a little bit of time to get these to click. Here we're going to see some Roman numerals, and sometimes people freak out with those Roman numerals, but they're actually helpful. If you find copper, which is element 29 on your periodic table, you see that copper is 2 or 1. The Roman numeral helps us know that we have copper plus 2 here, and then chloride, element number 17, chlorine is -1. So we're going to take this 1 and give it to copper, we get Cu1. We're going to take this 2 and give it to chlorine, and we get Cl2. So as a result, we're going to get CuCl2. Here we have vanadium. Vanadium is element number 23. Vanadium could have a charge of 5, 4, 3, or 2, so it's really got a lot. And so you start to see why these Roman numerals are important. V plus 3. And then selenide is selenium, or Se, and that only could have a -2 charge. We're going to take the 2 from selenide, give it to vanadium, so we get V2. We're going to take the 3 from vanadium and give it to selenide, and so we get Se3. Go ahead and pause the video, and I want to go through all of these. I want you to work through 7. Actually, I want you to work through 10. Okay. Here we have chromium plus 6, Cr plus 6. We have N minus 3. When you crisscross, you're going to get Cr3 in 6. 3 and 6 can be reduced to Cr1 in 2, which would probably be written Cr in 2. Tin 2 oxide, that is Sn plus 2, O2 minus. You're going to get SNO as your final answer. If you crisscross, you get SN2O2, and so we're going to reduce to SNO. Cesium is Cs plus 1. Nitride is N minus 3. We're going to crisscross, and we're going to get CS3N1, which is just going to probably be written CS3N. Calcium is Ca plus 2. Phosphide is phosphorus with a -3 charge. We're going to crisscross and get Ca3P2. Potassium is K plus 1. Sulfide is S2 minus. We get K2S. Okay? Now, if you're watching this from home, you probably don't have your you don't have your polyatomic ion sheet just yet. And if this is Unit 3 for you, polyatomic ions will not be on the Unit 3 test, so don't worry about having these memorized. I'm going to go ahead and write the ions here, and we have CO3 2 minus. That is what carbonate is. You haven't learned what carbonate is, and that's no big deal. Ammonium is NH4 plus 1. Phosphate is PO4 3 minus. Hydroxide is OH minus 1. Sulfate is SO4 2 minus. Sulfate is SO4 2 minus. And then acetate is C2H3O2 minus 1. These are all polyatomic ions. And if you think about what the word polyatomic probably means, poly means many, and atomic means atoms, and ion means ion. So a polyatomic ion is an ion that is composed of many different atoms. So for example, carbonate is carbon and 3 oxygens with all of those bonded in a way to have a -2 charge. Okay? At some point in chemistry honors, you're going to have those memorized. So what I want to do is I want to think about this 2, and I want to think about this 1, and I'm going to crisscross just the charges. I'm going to take the 1, put it down there, and I'm going to get CO3, 1. Now that's kind of confusing, okay, because that kind of looks like 31. So when you have polyatomic ions, please put them in, oops, I can't spell please, goodness. Please put their formulas in parentheses. Okay, so I have carbonate, I'm going to put that in parentheses. I have ammonium, NH4, I'm going to put that in parentheses, and now I'm going to crisscross the charges. I'm going to take the 1 of ammonium and put it down there with carbonate. I'm going to take the 2 from carbonate, put it down there with ammonium, and they're going to go outside the parentheses. So what this will simplify to is NH4 in parentheses 2 and then CO3 because we aren't going to have the 1 there. Aluminum is Al plus 3. Phosphate is PO4 minus 3. So what we're going to do is we're going to keep aluminum as is. It's not a polyatomic ion. It's just one atom. So we're going to have Al3. Now that we're starting to do phosphate, which is a polyatomic ion, we're going to do PO4 and put a 3 there. These guys will reduce. And we're going to get Al parentheses PO4, just like so. Aluminum hydroxide, we still have aluminum, Al plus 3. I'm going to keep aluminum not in parentheses. It's not a polyatomic ion. Then I'm going to write hydroxide in parentheses. That is just a polyatomic ion. I'm going to take the 1 from hydroxide, give it to aluminum. I'm going to take the 3 from aluminum, give it to hydroxide, and I get AlOH3. So I'm going to give you these ions. Go ahead, try out 14 through 17 on your own. I know you're at home and that you can just copy down my answer. That's not really my goal. My goal is for you to learn this while you're at home. Make the best of a cruddy situation. So if it's a polyatomic ion, meaning you can't find it on the periodic table, please put it in parentheses. On 16, we only have ions from the periodic table, so we don't have any polyatomic ions, meaning I'm not going to need to use any parentheses. Here we have NH4. Here we have C2H3O2. We're going to take that 1, move it there. We're going to take that 1, move it there. We get something that looks like this. Okay. Now, we're going to do this last section, then we'll call it a day. We want to write the correct name from each of the ionic compounds. Okay? So what we're going to do is we're going to find potassium on the periodic table. Potassium, is it multivalent? Look above it at the little number, and you should see K with a little 1 right below the number 19. It is not multivalent because I don't see more than one number, so this is just the potassium. And then fluoride, we want to just name it fluoride. Okay, this is how we need to know the anions. We find sodium, it is not multivalent, so we'll just call it sodium. And fluoride is still fluoride. We find magnesium. It is not multivalent, so I just name it magnesium. And then here we have chloride. Here I have magnesium again. And then I have sulfide. Magnesium's not multivalent. Remember, only metal cations could be multivalent. And number 5, I have cesium. And then I have oxide. Remember, anions are just going to take off the suffix and add IDE. On 6, I have hydrogen. And then I have sulfide. On 7, I have radium. And then I have phosphide. And we're going to see an exception here in just a second. On 8, I have strontium. And then I have sulfide. So I hope that those are pretty straightforward when they're not multivalent. Okay, so the metal we did not have a multivalent metal cation here, so we don't see anything with Roman numerals. Now, on number 9, we get chromium, element number 24. And when you look at chromium on the periodic table, it could have 6, 3, or 2. So we've got to figure out what version of this. So what I want to do is I want to reverse crisscross, okay? What I'm going to do is I'm going to take my 6 and I'm going to reverse it, and I'm going to get Cr plus 6. Chromium has a 1, so I'm going to get Br minus 1. This makes sense. If you find bromium on the periodic table, you only see that it could have a minus 1 charge. So what this is going to be, this is going to be chromium bromide, but because chromium is multivalent, we must specify which one of these charges it was, and it was chromium 6, so we'll put 6 after chromium in parentheses, and then we would call this chromium 6 bromide. We're going to do the same thing, nickel, which is element 28 on your periodic table. Nickel could have an oxidation state or a charge of 2 or 3. So this is going to be nickel chloride. We've just got to reverse crisscross, take the 2 from chloride, give it to nickel, so nickel plus 2. We're going to take the 1 from nickel and give it to chloride, Cl minus 1. So this is going to be nickel 2 chloride. We're going to see this another one, niobium, which is element number 41. We look at the periodic table, and Nb could be 5 or 3. So this is going to be niobium sulfide. When I reverse crisscross, the 5 goes to Nb, and the 2 goes to sulfide, which makes sense. Sulfide is always a 2 minus, so this is niobium 5 sulfide. Go ahead and practice these guys. Pause the video, and I'm going to write the answer for you. Again, you don't have to do these example problems, but I don't know how you get good at this without practicing and pausing the video. Okay, so those should check out. Now on 15, we find silver. So we're going to write silver chloride. Silver is not multivalent. I know it occurs in the transition metals, and that's typically where your multivalent atoms exist, but silver does not have more than 1 charge, so we don't need to give it a Roman numeral. If we call it silver 1 chloride, you're not wrong. You would not get counted off on that. It's just not necessary to have the 1 there. Okay, same thing with zinc chloride. Zinc is not multivalent. It could only ever have a plus 2 charge, and so that's fine. Now we get to this guy, and this one I've kind of messed up, because if you look at your periodic table, nickel could only have 2 or 3, and I've just goofed. We're going to take the 1 from chlorine and give it to nickel. This will be nickel plus 1. This 1 from nickel and give it to chlorine, Cl minus 1. So even though this doesn't exist according to your periodic table, if we named it correctly, this would be nickel 1 chloride. This guy would be nickel 2 chloride. This guy would be yttrium chloride. Yttrium, I know, also exists in the transition metals, but it only has a plus 3 charge, so we don't need to specify. And then 20 is really hard, and this is going to be the last one. We're going to take this 2 and give it to titanium, so we might say titanium plus 2 we're going to take this 1 and we give it to oxygen. We give oxygen -1. But this is fake, okay? This does not actually exist. If you look at titanium, titanium could have 4, 3, 2. So far it doesn't look like a problem, but if we look at oxygen, oxygen could only ever have -2. So if oxygen's really -2, that means titanium, to have the ratio, because it's 1 to 2, we must have titanium as +4. Okay, and this makes sense to me to call this titanium 4 oxide, because if we do the crisscross, we got titanium +4, we get oxide 2-, we crisscross them, we get Ti2O4. That would reduce, because they're both divisible by 2, to TiO2. Okay? If you've managed to watch to the end of this video, shoot me a Schoology message and say, Mr. Payne, I made it to the end of the video, and I will get you bonus points in your gradebook. Okay? Have a good one.